In lesson 30, we're going to talk about addition of vectors, and so this will bring in some of the things that we've done before with adding or with converting between polar form and rectangular form. So just let's quickly, if you maybe remember back from geometry, we kind of talked about vectors and how, if you had a vector, let's say like, looked like this, something like a vector is something that has both magnitude and direction, right? And so if we were to take and, put the terminal point or the initial point sort of on a coordinate axis, and then we could look at, there's a couple of different ways to represent this vector. So let's say the vector had length r, that would be its magnitude, and let's say it made an angle of theta right here with the positive x-axis, then we could put it in the form of r theta, that's its polar form. The other way that we could represent the vector is by a summation of its vertical and horizontal components. So if we went out from the origin, we went out x units here, and then that would be its horizontal component. And so we could say, x is its horizontal component, and I would be its horizontal. And then here it goes up y, that's its vertical component, so we could add on y for its vertical component. Okay, so these are, this is the rectangular form of the vector, this would be the polar form of a vector. Now if we had to take two vectors like, like 3i minus 2j, okay, and add that to another vector like 4i plus 3j, okay, we know that that's really easy to do when it's written out in this form, because we can just take the horizontal components, 3 and 4, add those and get 7 in the horizontal direction, and we can take the vertical components of -2 and +3 and get a +1 and just put those together. And this was what's called the resultant. Okay. So if we have everything written in our rectangular form, it's just easy. You add the horizontal, you add the vertical, and you're done. However, if we have them written in this form, it's not as easy. So let's look at an example of how we might do it if it's written in polar form. So let's say we wanted to find the resultant of these two vectors written in polar form, 4, 20, and 7, -230. Okay, if we were to just maybe draw a little sketch of what's happening on the side, okay, so we have this, so we have an angle of 20 degrees, and we go out 4, so maybe it looks something like this with a 20-degree angle and a length of 4. And we're going to add to that an angle of -230, so I guess we would go -180, and then another 50, that would be at -230, and it would be 7. So that looks like, okay, just pretend. All right, so if that's 4, maybe that's 7. Maybe this is too long. Okay, and then we would need to take these two vectors and imagine, okay, if you'll, again, like imagine we, back to your geometry days, remember we did the parallelogram method and different methods to find the sum of vectors. Okay, but you can, so imagine if we were to draw a parallelogram and complete the diagonal in a maybe, it looks like, maybe something like this. Okay, so maybe so we would say, all right, you also can imagine you had a force pulling this direction and a force pulling this direction, and you had a box here. Okay, what path would the box take? Well, it wouldn't go along this one, it wouldn't go along this one, it would go along something else. So let's say it goes along this way. Now, I don't know, my picture isn't very accurate, maybe it's here, I don't know, it's somewhere in there. But we're looking for that resultant vector that would be produced by these two. So the easiest thing for us to do is convert both of these to their rectangular form, add them in rectangular form because that's really easy to do. But then we're going to have to convert them back to polar form. So fortunately, we're good at these conversions now, and we just have to be able to do that. So we have this first vector. This is, I'll just call it vector 1. Okay, so vector 1 is going to have its x value and its y value. Okay, and we know the way that we find the x value is to do r times the cosine of theta, which for us is 4 times the cosine of 20. And the way that we find the y is we do r sine of theta, which for us is 4 sine of 20. Okay, so let me grab the calculator. So when we do 4 cosine of 20, we'll get about 3.76. And when we do 4 sine 20, we get about 1.37. Okay, so that's vector 1, that's this first vector. And now we'll have to look at vector 2. Okay, it's got an x and a y as well. So this is going to be 7 cosine of negative 230, and the y is going to be 7 sine of negative 230. So our 7 cosine of negative 230 is about negative 4.50. And our 7 sine negative 230 is about 5.36. Okay. So now, you know, this one, x1 and y1 would give us, you know, this is like about a 3.76 right there, and 1.37, you know, right there. So that's sort of where the end of our vector 1 is, and this one right here, negative 450, like this is our negative 4.50, and the 5.36, that would be about right here. Right, so that's the second vector. Now what we really want is this one, the resultant. Okay, so how are we going to find the resultant? Well, the x, or the horizontal component of the resultant, we're just going to add together x1 and x2, so the horizontal components from the two vectors that are being added. Okay, so for us that's 3.76, and then plus negative 4.50. So if we have our 3.76 minus 4.5, that gives us about negative 0.74. And then the resultant, the vertical component of the resultant will just be the sum of the two individual vertical components. So we have our y1 plus our y2. So that'll be about 1.37 and about 5.36. So if we do our 1.37 and our 5.36, we get 6.73. Okay. And so looking at, you know, my picture here, it's not super bad. So, you know, this right here is our negative 0.74, and it goes up to 6.73. That would be our resultant. Okay. Now, that's in its rectangular form. But you see how they gave them to us in polar form. Well, they want the answer in polar form as well. So we're going to have to take this rectangular form of, you know, the negative 0.74i plus 6.73j. And we're going to have to convert that back to its polar form. So its polar form. Of course, we note from our picture here that it's in the second quadrant, and so we know like that it's not going to give us exactly what we want because we've done these before, right? If it's in quadrant 1 or 4, we can get but the inverse tangent never gives us something in quadrant 2 or quadrant 3, so we have to make sure that we're thinking when we figure out the final form of these. All right, so our form, we need an r value, which is going to be the square root of our x, or our horizontal component squared, plus y squared, our vertical component squared. For us, okay, our horizontal is negative 0.74 that we have to square, and our vertical is 6.73. Okay, so if I do the square root of negative 0.74 squared plus 6.73 squared, I get roughly 6.77. So that's my r value. And then my helpful theta is going to be the inverse tangent of the y value over the x value, which for us is the inverse tangent. The y is 6.73 and the x is negative 0.74. Okay, so if I do the inverse tangent of 6.73 over negative 0.74, okay, I will get roughly negative 83.73. Now think about what this means. Okay, negative 83.73 is going this, right, is in the fourth quadrant. I'm not thinking about a vector that's in the fourth quadrant. I'm thinking about a vector in the second quadrant. So what's really happening here, right, is we're getting this angle right here is not my negative 83.73. But I really want this angle over here. Like that's, I want this vector. Okay, but so I just need to make sure that I subtract this from 180. So I'm really looking at this 96.27. Okay, so in polar form, I've got the 96.27 as my angle and my 6.77. Okay. Now again, if you have a little picture, you can verify that that makes sense. Okay, I'm a little bit, 90 degrees here, and I'm going a little bit past that because I'm right here in the second quadrant, just barely in the second quadrant. Okay, and then I have this 6.77. Okay. All right, so that is the process that we would have to go through to find the resultant of two vectors that are written in their polar form. First, we convert them to rectangular form, add them in rectangular form, and then convert them back to their polar form. Okay, so another similar problem that we'll look at is finding the equilibrant of two vectors. Okay, so we just looked at finding the resultant. Now we're looking at the equilibrant. What is the equilibrant? Well, if I went back to this picture, the equilibrant is basically, imagine you're playing a game of tug of war, and there's one team that's pulling in one direction and another team that's pulling in the other direction. If they pull in the exact opposite direction with the exact opposite force, nobody will go anywhere. They'll just be at a standstill. That's what the equilibrant is. So here's the resultant, and then, okay, so if I went exactly in the opposite direction, okay, so like this one had a angle of 96 point whatever it was, 27. Okay, and if I went in the exact opposite direction at negative 83.73, okay, and then this one had the length of 6.77. And if I went in the exact opposite direction at a force of 6.77, okay, this one would be pulling this way, this one would be pulling this way, and we wouldn't go anywhere. So this one right here would be the resultant. This one over here would be, sorry, this one over here would be the resultant. This one down here would be the equilibrant. Okay. So what you can see is that there's always going to be 180 degrees between the resultant and the equilibrant. Oh, I just can't get this right. Equilibrant. This is the resultant, the one you get when you apply the forces. The equilibrant is the one that would allow it to not go anywhere. Okay. So with that in mind, let's do this problem. Okay, so in order to find the equilibrant, basically we have to find the resultant first, and then we know that the equilibrant is just 180 degrees away. Okay. So let's go through the process. Let's find vector 1. So we have our x1 and our y1. Our x1 is going to be 4 times the cosine of 50, and our y1 is going to be 4 times the sine of 50. And then when we do our vector number 2, its x and y values. This will be -6 cosine 170, and this one will be -6 sine 170. So let's just put all those into our calculator. Okay, so we have 4 cosine 50, which is about 2.57. We have 4 sine of 50, which is about 3.06. And then we have our -6 cosine of 170, which is about 5.91. And our -6 sine of 170, which is -1.04. Okay, so first thing we need to do is find the resultant. Okay, so the resultant, we're going to just add the, oops, this should be 2. We're just going to find the sum of the two x values, so we'll do our 2.57 plus our 5.91. And we get 8.48. And our y value will be our 3.06, and then minus our 1.04. And we get 2.02. Okay. So in rectangular form, we would have 8.48 plus 2.02 J. But of course we know that we want that in its polar form, so let's find this in polar. So our R value is going to be the square root of 8.48 squared plus 2.02 squared. So we'll do the square root of 8.48 squared plus 2.02 squared. And that will give us roughly 8.72-ish. Okay, and then let's think about where this is if I had to draw this. Okay, 8.48 would be over here somewhere. 2.02 would be up here. So we're looking at something in the first quadrant, right? This is quadrant number 1. Of course, the nice thing about quadrant 1 is when we do our inverse tangent, it gives us the perfect angle that we want, and we don't have to do anything to doctor it up. So it's always nice to get one of those first quadrant angles. So the theta that we need is just going to be the inverse tangent of our y value of 2.02 over our x value of 8.48. Okay, so the inverse tangent of 2.02 over 8.48 is going to be about 13.40. Okay, so in our polar form, that would be our angle of 13.40, and our 8.72 is our magnitude. Okay, this is the resultant. Okay. But remember, what they asked us to find was not the resultant, but the equilibrant. So the equilibrant is going to be over here, going in the opposite direction with the exact same magnitude, so this 8.72 magnitude, but going in the opposite direction. So imagine I just need to be 180 degrees away. So what angle is that going to put me at? Well, we can just take the angle that we had here, the 13.40, add the 180, and we'll see that the sum total, so this is going to be the polar for the equilibrant, Okay, it's still going to have a magnitude of 8.72, but the angle is going to be 180 degrees different from this one. So it's going to be 193.40. Okay. So the way that you'll find the angle for the equilibrant is you'll always either add 180 or subtract 180 depending on what number you have here. So if this is greater than 180, you would subtract 180. If this number is less than 180, then you would add 180. So we always want to have a positive number here. It's easier for us to understand these when we have two positive values. So that's our goal. In order to ensure that the angle here is positive, you just have to look at this one. Okay, if it's less than 180, then you'll add. If it's greater than 180, then you'll subtract to get that number. All right, so that is the process for finding both the resultant and equilibrant. We've already done a lot of conversions between polar and rectangular, so hopefully these won't give you too many problems.